I successfully changed my password on Saturday, and I'm having all kinds of email trouble. So I sent some messages. I don't know if they went out. Sometimes I'm receiving some messages, but I just wanted to warn you. We probably have a quiz due this week. Mm-hmm. Yeah. So I've been working with ITACs, but I don't know when it's going to get fixed. Okay. So you might want to call if you want to schedule an appointment to see me. You may want to call. Okay. I don't know about the email.
I'm having trouble too. I can't even get on the internet with this computer. And I'm getting all kinds of password stuff popping up.
Wow.
You're probably not alone.
Ah. Okay, I don't know if that's good. I don't know if it makes me feel better.
Hackers.
Okay, so we're going to continue with hydrophones today and this week. Okay, now we're getting near the end, so hopefully I'll be sending out email messages to you about due dates. Okay, and there's an experiment this week, right?
Yeah.
Right. Okay. Okay, so we looked, where we left off with last lecture was, it was a review of determining sensitivities for hydrophones with equivalent circuits. Now we want to use the, I guess this is also a partial review. We've done this before too. We want to determine the sensitivity using the piezoelectric relationships. Now we're going to take this. This will be pretty simple right now, but starting later in the lecture, it's going to get more complicated and more practical. Okay. And we're going to deal with different shapes and different polarizations. We're going to make the standard assumption that the wavelength is large compared to the size of the element, size of the hydrophone. So there's only uniform compression and expansion going on there. It's essentially quasi-static. There's no standing waves, right? The acoustic pressure is going to be uniform. Now, we will deal with shielded. We'll assume that some surfaces are shielded, and you'll see how that works. Okay, but because of the long wavelength in the liquid too, the water, the pressure is going to be uniform on the exposed surfaces. It'll be uniform. That's a nice, it's a really nice simplification. So we're going to do a rectangular block right now, and then we're going to get into a cylinder. And this is the favorite configuration. We'll get into that in depth. We won't finish it today. We'll do more tomorrow. And it's actually interesting, as you'll see. Okay, so here's a rectangular block. It's poled in this direction. The polarization is direction, and it's electroded in this direction. Electrodes, on top and bottom. And we're going to assume now that we have the same pressure on all faces. So none of the surfaces are shielded from the sound wave here. We have the usual rectangular dimensions. You can see this isotropic pressure exerted here. Okay. So on the 1, 2, and 3 surfaces, there will be a uniform stress. It will be identical to the pressure. And you remember why the minus sign here. Positive stress is to elongate it, and the pressure is going in the opposite direction, so that's why I have the minus sign there. So it's convenient here to use the set of piezoelectric relationships where T and D are the independent variables. Remember, there's 4 possibilities for all the variables. We mainly stuck with, what do we used to, I think I mentioned it in here. Yeah, we usually stuck, For a long time, we just used T and E. All right? So we're going to do T and D now. And the reason is, the stress is, T is nice because we have this nice simple stress here. And the displacement field is, of course, 0, right? Because this is a hydrophone, it's operating, there's no free charge. So D is equal to 0 in all directions. So when T and D are the independent variables, here's one of the piezoelectric relationships for the electric field in vector matrix form. So this is a 3-vector, right? Remember the stress here is a 6-vector, 6-dimensional, okay? So that means G has to be, 3 by 6 matrix. Beta here is just a 3 by 3 because D has 3 dimensions and so does E. Okay. So if we look in to get the sensitivity, we want to look in the 3 direction. We look at the 3 component here, and so written out, if you write out all the components, here's what we get. Setting D is equal to 0. Here's what we get. The stresses are all the same. They're equal to minus P. So this is the electric field. Now, you'll see going from here to here, what's happened, I've substituted, hydrostatic, same stress everywhere, minus P. And also, because we're dealing with a ceramic here, it's got axial symmetry around the polarized axis. So G31 has to be equal to G32. We'll just call it G31. So we just pick up a factor of 2 there. The voltage here is just going to be the electric field times the distance. We're assuming a uniform electric field here, which is actually a good approximation if you don't make it too big, right? Because of the large dielectric constant. Remember we talked about that? So it's actually not a bad, it only took me like 3 years to understand that. So this is actually, I think, a pretty good approximation. As long as you don't have the 2 plates, too far apart. So we're done. The open circuit sensitivity is the voltage divided by the pressure. The voltage is just this times the distance. We divide by the pressure, it scales out. This is all linear, and we have our sensitivity. So let's plug some numbers in now. This is type 2, PZT, Navy type 2. In the book, from some chapter. Plug these numbers in. And you'll see what happens here. The G31 is negative, so we're going to have competition here. Furthermore, look at the magnitudes here. Okay, there's competition because of the negative sign. If you look at the magnitudes, if you double this, you're going to get somewhere around 22. It's going to be, you roughly get cancellation. You see, so we're losing a lot because of that. To compute the value, we need a thickness here. So typically what people will do is assume 1 millimeter thickness, and this is what we get. And you can see it's microvolts. It's roughly microvolts. Now microvolts by itself is not necessarily a bad thing. It's all relative to the noise. Microvolts can be preamped up, and there's no problem transmitting it with picking up the noise. However, if the noise is at the same level as the signal before the preamplification, it's not going to do you any good. Okay, you're in trouble. Now, this is for 1 centimeter thick, and if you're thinking about designing a hydrophone or purchasing one with different thicknesses, the natural way to express the answer is the sensitivity per unit thickness, because it's proportional to the thickness here. So a better way of stating the result is 20 microvolts per Pascal centimeter. So to get the sensitivity, you have to just multiply by the thickness, which is easy to do. Okay, so as I mentioned, we have competition here. The G coefficients are of opposite sign. And okay, so what that means is, if you compress this thing, A compression is going to decrease the electric field here, but a transverse compression is going to tend to increase it. We're getting competition here, and consequently a small sensitivity. Now, so if that's a problem, what you can do is you can try to shield the other surfaces. Remember we talked about that some time ago? If you, for example, if you shield the non-poled, you shield it here on these sides here, then there's no contribution. So it's not subject to that stress, to the pressure. Then this is gone. And you can see you're going to get, it's probably an order of magnitude or more. It's going to make that a lot bigger. The other thing you can do, the textbook talks about the shielding in different places. I'm not so sure how easy it is to do that, all right? But there's other things you can do here. You can try different material, right? So you can see that what's relevant here, and we talked a little bit about this before, you can see that in this problem here, what's relevant is this combination of the G coefficients, okay, for this hydrostatic case. You're adding them all. We get 2 here because they're the same. It turns out, as we'll talk about Wednesday. Yeah, I guess it's Wednesday. So Wednesday we'll talk about this is, okay, let me back up here. So this is the relevant quantity. So let's just call that G sub H. All right. It turns out, and we've mentioned this once before, that it can be shown that a better figure of merit is not just this, but is to multiply it by D. And we'll look into that a little bit later. But this is the typical figure of merit. You want to maximize this for a hydrophone, okay? And it's so important that people have values for different materials, and some of them are in the textbook. So if you look at these values, you'll find that some are like 100 times greater. This figure of merit is 100 times greater. So I made a little bit of a mistake here. So if the D, I need to add here, if the D values are roughly the same, if you find a material that's 100 times greater for this figure of merit, if the D values are the same, then you're going to get 100 times your sensitivity will be increased by a factor of 100. That's huge. Often sensitivity, a factor of, this is my experience, limited experience in this, is sometimes a factor of 2 can make all the difference in the world in an experiment. That's happened to me. So anyway, but you can also find the G values. So this is one way of, this is a standard thing that people do in hydrophones. Use different materials. Okay, so that's simple, that's the cube. It's not really useful, and we'll see some evidence of that. What's really useful, as I've mentioned before in hydrophones, is cylindrical, and more specifically annular. Okay, so that's what we're going to look at now. We're going to look at this like I said, in depth, because this is the popular geometry. And it's really interesting how it's handled, as you'll see. So here's the idea. We have an annular cylinder. It's got an inner cylindrical surface of radius A, an outer of B, and it's got a length script L. You want to remember this. This is the standard notation: inner radius A, outer radius B. Right? It's sort of standard for just about for any annular geometry anywhere, I think. Usually A is the inner radius, B is the outer. So it's good, as you'll see. It's just good to memorize this. I think you'll do it naturally, and you'll see why as we go on. Okay. So this is the Z direction. Is the Z direction is going to be the axis of symmetry. All right. Now there's a little bit of a problem here, and I'll remind you when we get deeper into this. We don't necessarily want to polarize it. We can polarize it in this direction. We can polarize it in the Z direction and electrode it, okay? But we want to be able to deal with other possibilities. For example, polarizing it radially and electroding the inner and outer cylindrical surfaces. We will keep calling this the z-axis even when we have radial polarization. So it's a little bit of a problem, but people get around it. We choose the 3 direction to always be the direction of polarization. So up until this time, now 3 and z have been the same, and it's always been the pole direction. Well now, because we have an axis of symmetry here, and we want to deal with radial polarization, as another example. There's also azimuthal polarization, as you'll see, interestingly enough. So here's right here, and I'll pass this around later. So we'll stick with z being the axis of symmetry, and I'll remind you about this. But we want to be able to deal with different polarizations. So now z is not necessarily the axis of polarization. It's the axis of symmetry. We're also going to consider different exposures to the sound wave. We can have one or more shielded surfaces here. And we'll go through this explicitly. So the way we're going to calculate this, and we can't do everything. If you want to get more information, you can look. There's more information on this in the book. It gets a little involved. The idea of what we're going to do here is we first calculate the response of the cylinder. We calculate the stress due to the acoustic pressure, the stress in the cylinder. And from that we get the electric field. And then from the electric field we get the voltage. Then we can get the sensitivity. Now that may sound like what we've been doing all along, but we actually haven't been doing that. When you compress a piezoelectric, you can change the bound charge. Right? Remember those, remember this? All the bound charge here? In a piezoelectric, when you compress this here, you can, and then there's a net positive bound charge here, and going to be a negative on the other side here. When you compress that, you can change the bound charge, which changes the electric field. The electric field depends upon that. Okay? So, and in fact, for a hydrophone, that's where the electric field's coming from, because there's no free charge. Now, so this is actually an approximation, what we're doing here. We're doing this in sort of, it's kind of like successive approximation. Maybe I shouldn't say anything. So the way we're doing it here is actually an approximation, because we're neglecting the effect on the bound charge. Now, what we're neglecting here is, and I need to, I don't know if I said this right, let me say it again. There is some bound, when you polarize it, there's going to be some bound charge. There's going to be an electric field. Okay? So when we compress and expand this, there'll be changes in the bound charge. That's what we're going to neglect here, is the changes in the bound charge. And so I guess what, you know, I'm going to have to think about this, but I guess so what we're taking into account here is the voltage, the change in voltage is just going to be due to the change in distance. I think that's what this is saying. I need to check this and look in the book. Let me check this. Anyway, in the past, we've always done this simultaneously. We've done everything. We've solved the piezoelectric equations simultaneously. We found a solution. There's no contradiction here. But this is actually a sort of successive approximations. You can kind of think of it, that it could be done successively. You can get more and more accurate. We are making an approximation here, and I'll check into this. Okay, so we're at low frequencies. So determining the stress, there's a bit of a problem here, okay, when we subject this thing to this pressure, to this external pressure. The stress doesn't have to be uniform in this. It's not in general uniform in this geometry, as you'll see. But one thing you want to notice, of course, is, let me just remind you that when we subject it to this oscillating pressure, the problem of determining the stress throughout the solid is a quasi-static problem, because we're way below any resonance here. We can treat this quasi-statically. So the fact that we're doing this at some frequency doesn't make any difference from just doing it extremely slowly. Okay, so that's nice. That simplifies everything. However, even statically, this geometry can be complicated. Okay, it turns out, like I just mentioned, as I just mentioned, that the stress is not uniform throughout the material, and for us to derive what the stress is going to be in the cylinder, we would have to go back. We don't have enough theory. We didn't do enough theory of elasticity to do this. If you're interested in how it's derived, you can look in the book. Okay, we're just going to use the results, and the results are actually pretty simple here. Here's the result. So, this is absolutely general for any annular cylinder geometry. Okay, so you have any annular cylinder, and this is just theory of elasticity here. Nothing to do so far with electrical properties or piezoelectric properties. This is purely elastic. The general form of the stress is given in the radial direction, okay, is that it depends upon R. And A and F are constants that depend upon the boundary conditions. Now, one way, I was thinking about this, one way to appreciate the fact that there's radial dependence here is that because we're in the quasi-static limit is fine for us. If you look at an element of the solid, it has to be in essentially equilibrium, I think, okay? So all these stresses need to add, and that's exactly, it's exactly true in the static case. It has to be in equilibrium. So because of the radial geometry, if you look at a little element here, now this is just supposed to be a little element of this bigger, cylinder here. All of these stresses these stresses are going to have to balance, all right? And there can be no torque too. So it's going to be, it's very natural to suspect here, because of the radial geometry, that there's going to be a radial dependence. And here it comes in right here as 1 over R squared. The same thing happens. You can see there's a connection, what's going on radially here, what's going on here. These two stresses here don't add to 0, right? Because they're at angles here. So there's an interplay between the azimuthal and the radial. So maybe it's not surprising that so it looks like this. Okay, same A and same F, which depend upon the boundary conditions, but with a minus sign here. Finally, the longitudinal direction is simple. It's the same as if it were a block. It's constant. The stress is constant, which is what we've been dealing with up till now. Okay. So here's where it gets interesting, I think. All right. We want to be able to handle, for the annular cylindrical geometry, we want to be able to handle different polarizations and different exposures to the acoustic wave, to the sound wave. So there are many possibilities. There are 3 standard ones, and they're in the textbook, and later tomorrow we'll be looking at graphs, okay? So they're labeled A, B, and C. This is just like in the textbook. Case A refers to this has to do with the exposure to the sound wave. Case A has to do with only the outside cylindrical surface being exposed. So capital A, yes. It's not lowercase, okay? So only the outside cylindrical surface is exposed to the sound wave. Not the inside and not the ends. Okay, that's case A. Case B is the outside and the ends of the cylinder, okay, at Z is equal to 0 and L, but not the inner. Case C is similar to B, except there are end caps. Now, why would that make a difference? If I have here's my annular cylinder, and I expose, the material is exposed to a sound wave here and here, okay, on this surface right here. If I put an end cap here, why is that different? It's pretty obvious. Yeah, there's going to be a greater force, a greater pressure. There's actually a sort of a scaling up, a magnification of the pressure, because you now have, you have the same area, right? But the force is now beefed up because you have this rigid end cap here. So effectively the pressure is going to go up. So this is a popular thing to do. So that's going to be case C. All right. Now, as I mentioned, there are many other possibilities, and also there's different polarizations, okay? So it wasn't until 1977, that's roughly 40 years ago, a little less than 40 years ago, till somebody unified essentially all possibilities into one set of formulas. So here's the idea. It's actually, when you see it, you go, well, yeah, of course, it's a natural thing to do. But, you know, nobody did it until 1977. Oh, and if you want to look at the article, I probably have it on my computer. Brian I'm sure he references this, because that's where I must have gotten this year. So it's probably a JASA article. You can get it. And incidentally, you know, if you're on a campus computer, you can go right into the Acoustical Society of America website and get any paper you want. I don't think that works if you're not on camp, you know, if you're not going through campus. Does anybody have we talked about this before? I talked to recently someone about it. Well, recently, I don't know. Yeah, so this is something you want to be aware of. It's useful. I'm sure. Haven't I mentioned this to you guys before?
You and I have talked about it in our meetings.
Oh, okay. Not okay. Yeah, it's a good thing to know. You're doing acoustics research. Yeah, you want to get papers instantly, you know, and free, right? That's the way the world is now, and there are. But you can't always do that, as I'm sure you will know. But you can do it for jazz on here. So here's the idea. There are, I call them exposure parameters. That's my word. I just want to warn you. There are these three exposure parameters: alpha, beta, and gamma. Okay? So here's the meaning. To quantify all this. If alpha corresponds to A, the inner radius. If alpha is equal to 0, that means you're not exposing the inner surface here. If alpha is equal to 0. If alpha is equal to 1, you're fully exposing it. If alpha equals a half, guess what that means? Anybody? You're just, you know, it's like you're not exposing half of it. All right? So, now that would be very unusual if that is useful, but it's different when we get to the end caps here, as you'll see. So these exposure parameters here can run from, in this case, for alpha, it runs from 0 to 1. Okay, 0, it's not exposed at all. 1, it's fully exposed, and it can be somewhere in between. If it's free, remember a free flooded hydrophone like this, it will be exposed to the pressure, to the sound wave. Beta is essentially the same for the outer cylinder, the R equals B radius. So remember, this is the R is equal to B radius. Beta is equal to 0 means you're not exposing the outside cylindrical surface. B equals 1 is you're fully exposing it. Gamma refers to the ends, and it's the same idea, If gamma is equal to 0, there's no exposure. If gamma is equal to 1, you're exposing this. If you put an end cap on here, what do you think gamma is going to be? Greater than 1. This is where it becomes important. And we will actually do a homework problem on that so you can see how it's calculated. It's very simple, but we're going to do a homework problem on it. That'll be Thursday. Okay. All right. So why is alpha, beta, and gamma useful? Because we can codify, or quantify the exposure here. The boundary conditions at R is equal to A, the stress will just be minus alpha P. When alpha is equal to 0, there's no stress, it's shielded. When alpha is equal to 1, it's fully flooded, But alpha could be like 1/2. It could be half flooded. All right. Similarly for R is equal to B and at the end points. So now the next step, we're not going to go through this, but the next step is to take these boundary conditions here and impose them upon the general stress in the cylinder, neglecting the piezoelectric action here. We impose the boundary conditions on here. And the effect of that is we eliminate A and F and G. They're going to be gone. Instead of those 3 parameters, we now have alpha and beta and gamma, which are useful, directly useful for us. So the result of that calculation, let's see. Well, we've already talked about this. Okay, the negative sign. We talked about that. There is an e to the I omega t here, but because it's quasi-static, it's just implied here. There's no reason to carry it along. So it's assumed, it's understood. So when you apply the boundary conditions at the bottom of that previous page, you essentially get rid of A, F, and G in terms of alpha, beta, and gamma, and here they are. Now this is complicated, but it only needs to be done once. See, once you've done it, then you just put in the alpha, beta, and gamma of what you have. And it's very general. These alpha, betas, gammas, there's a wide range of possibilities there. So let's look at an example. Suppose, to see how this simplifies when we look at any specific case. And typically we'll simplify a lot, like in this example here. Alpha is equal to 0, so the sound's not getting inside, it's shielded, the inside. It's not flooded. Okay, alpha is equal to 0. And let's say we shield the ends. That means gamma is equal to 0. And then beta will be 1. That'll be the only non-zero exposure coefficient. So you just look at these equations. You can do this in your head. Set alpha and gamma equal to 0 and beta is equal to 1. And then you get these. This is going to be the stress in there. Okay, now so far this has just been pure theory of elasticity. We're neglecting the effect of the electric field. The electric field is going to have an effect on the stress because this is a piezo ceramic, right? Piezoelectric material. So at this point, to go any farther, we now have to specify what's going on electrically. We need to, first of all, specify the polarization. There are 3 sort of standard useful polarizations for yes.
So, but everything up to what we've done right now, we can do without considering the polarization of the material?
Yeah, we're neglecting the effect of the polarization on the elasticity.
Okay.
Yeah, which apparently is a good approximation. I think that's all that Brian says about that, but I can't remember.
So essentially we can consider the geometry of the situation, apply this theory, and then go to the
we deal with it mechanically. We're dealing with it separately. Before we dealt with them together in our piezoelectric equations, simultaneous solution. Right. Now, so let me make a statement about this. So you may say, well, what if that is not good enough? What if you want to be more accurate? Do you have to just now solve everything simultaneously? No. What you can do is, you can do what's called, I mentioned this phrase before, successive approximations, okay? You can, and I wouldn't be surprised if people have done this, I don't know, but you'd imagine doing this, neglecting the electrical stuff. Then you choose a polarization, and knowing what this is, you can calculate then what's going to happen electrically in there. And then you can go back and modify and get an improved approximation for this. And you can keep going back and forth. This is the idea of successive approximations. It's also called perturbation theory, but students are afraid of the word perturbation theory because they always, and everybody goes through this. But so that's why I often call it successive approximations. And I know it sounds probably a little ambiguous to you right now, but it's a pretty simple idea. You just make a pretty gross assumption, make some progress, calculate the effect, and then go back and refine your initial thing. You go through the successive approximations, and then you can just keep doing that. And usually it converges, not always. And usually people are not interested in carrying it too far anyway. So this is a basic idea in all of physics. You name it. Quantum mechanics, especially nonlinear analysis, where you almost always you can't do anything exactly analytically. So people use perturbation theory, successive approximations. Okay, so here are the three practical polarizations. There's, as we mentioned before, there's radial polarization, okay, when the electrodes will be on the inner and outer cylindrical surfaces. There's longitudinal polarization, where the electrodes are the ends here. And then there's a segmented azimuthal polarization. So there, and we'll talk more about this, but the idea there is, for example, these are, it's going to get me in trouble. So you have these different regions here, where you have electrode, you can imagine planar electrodes here, running down here, separating these different segments. And you have to alternate the polarization, just like we talked about before, remember the longitudinal segmentation, where you have to alternate, otherwise you're not going to get anywhere. And we'll go over this some more later, okay? So that's the tangential polarization with azimuthally positioned electrodes. And again, we'll go over this in depth tomorrow. Now, let me just point out right now, for the azimuthally segmented case, or whatever you want to call it, you'll hook these up to, let's say, the positive terminal, and these up to the negative terminal. And you have to have an even number. You can't have an odd number. I'll let you think about that. But you got to hook, this is going to be, so this will be like plus and minus. You got to have an even number. Or it won't work. So here's there's a diagram here. So this is n is equal to 1, 2, 3, 4, 5, 6, okay? Yeah, this is a lot better than what I'm doing, okay? I forgot this was in here, sorry. So here we have these, I guess Brian's calling this typical because there are other electrodes here. I think he just, well, anyway, so these are all electrodes, and you alternate the sign, all right? And the polarization here will look like this. Now, how again, I think we've talked about this before, but this is very appropriate now to get into a little bit more depth. This is going to be PZT, usually. Not always, okay? But usually it's PZT. And in the construction, I think what they do is, if you construct this without it being polarized, and then you zap it with a very large DC field. And what effect is that going to have? Well, here it's going to polarize this material this way, right? Over here, the opposite way. So you end up with segmented material here that's polarized, in the opposite direction. It alternates just as the electric field alternates. And you need that, right? Because when a sound wave comes in and you get a compression here and you get a change in voltage, you want to get you want the change in voltage here to add with the change in voltage here. And if you don't alternate those polarizations, they're going to cancel. They probably won't cancel exactly just due to the non-uniformities, but approximately they're going to cancel. So you've got to alternate them. But it's natural, you know, because I suspect that the polarization here occurs after the electroding. I'll bet that's very common. It seems very natural. You know, if you're going to polarize some material, you need some electrodes. Well, why don't you just use the electrodes you're going to end up using in the end, right? It's pretty obvious. So I think that's what they do. Now, there's something else here. If you actually, so far we've been talking about, you know, genuinely segmenting this. This is a different piece than that. There's an electrode in between, okay? That's hard to do for a hydrophone. Hydrophones tend to be small. So somebody realized a trick here, all right? They don't, this material this is all one piece. And what they do is, they put a ribbon, they paint it or attach it somehow, this conducting ribbon on the outside and inside. And I'm going to pass this around, I want you to look at it. And there's one place where you can see it doesn't quite line up. That's a dead giveaway, that this is not genuinely segmented. It's just they've put this outer conductor on the outer surface here. All right? So let me just pass that around. So and it's probably done because it's a lot easier to do that than segment a hydrophone. And hydrophones tend to be small. Projectors, I think they tend, because you want to get a lot of power out, I think those tend to be genuinely segmented, the projectors. And they may always be segmented, I don't know. But it's a common trick in hydrophones not to segment them, but to just have the electrode, the conductor, is just on the outer surface here. It doesn't penetrate through here. Now, so what happens when you then zap it and you polarize it? What's going to happen? If I don't have a genuine segmentation here, I'm going to get the alternate polarization. Is it going to be as strong as the other case? No way. Okay? However, people have found that they can sacrifice that, and Brian mentions this number here. Typically, so it's not going to be as sensitive because you're not going to have this strong polarizations as you would if it was genuinely segmented. But the effect typically, the loss of sensitivity is effectively only roughly as much as only 15%. So people, that's okay. Okay, I think for all or nearly all applications, it's much easier than have to genuinely segment this thing. We passed around hydrophones, segmented hydrophones before, I think. I think in the past I passed around the longitudinal ones rather than the azimuthal ones. But for you guys, I passed around, I think there was an azimuthal one. Remember that? Kind of a beefy thing. Those things can be really expensive, incidentally. And a lot of work goes into there. They can easily cost thousands of dollars. Just for that. I'm not talking about electronics. It's just a projector. I think remember it was about this big, quite heavy, and it looked like it was genuinely segmented. Yeah, those things can be quite expensive. Okay, let's see, where are we? God. Okay, so what we're going to do here, it's appropriate to stop before we need to specify 3 different basic types of polarization and carry on with our calculation here. Okay, now that we've got this, now we need to specify the polarization. And we'll start to do that tomorrow. Let me just warn you, there's one more thing here, and I've already said this, but We keep the z-axis as the axis of symmetry, but the 3-axis will always be in the direction of, as far as I know, it is always in the direction of polarization, no matter what. It's kind of a strong statement, but it's true at least for this course. So tomorrow we'll begin with the radial, and we'll go through the different polarizations, and we'll get, Brian has graphs of sensitivity versus the particular the relevant geometrical factor here. And interesting things happen. You can see there's interesting structure here. Okay, anybody have any questions?